All right, we are on chapter 3, and we're going to talk about compounds and how elements combine. And this is really important because when we think about all the substances around us, like, for example, water. Why is water water? Well, it's specifically, right, H2O. So why is it that combination? Why isn't it H3O? Why isn't it H2O4, right? Why is it that specific combination of atoms? And what we're going to find out is that there's an advantage to combining atoms together, right? And the reason that all these atoms want to combine is they want stability. And so we're going to talk about how that combining of atoms leads to stability. And so we're going to go through a couple of different sections. They've broken it down pretty nicely for us. So we got 7 sections in this chapter. And we're really going to use the periodic table to understand why elements combine. And so you have to remember that certain kinds of elements are going to combine in certain ways. And so you're going to form ionic compounds with certain elements, and then you're going to form a different kind of compound, a covalent compound with other kinds of atoms. And so we're going to have to make sure that we know how they combine and why. So let's move on a little bit and let's talk about electrons, because electrons control why atoms want to combine, right? So last chapter we talked about the nucleus and what was going on there, and now we're moving out into that electron cloud, and we're going to figure out what that is, right? Because remember, if this is our nucleus and here's our big old electron cloud, the electrons aren't filling the cloud, but what we can say is that the electrons are likely to be found in all of this shaded area that I'm shading in. We're more likely to find electrons there, right? It's really difficult to determine the exact location of an electron. They move very fast and kind of crazy, and so what we do know is that we can find them in this general area, right? And when atoms combine, they're going to rearrange electrons within that cloud into a more stable configuration. That's the whole point of combining, of making compounds. And so when they do that, you got to remember that electrons are always moving around. And because they're moving around, they have energy. And the more they move around and the farther they get from that nucleus, the more energy they have. And that's a really, really important concept to remember. So remember, electrons that are farther from the nucleus have higher energy, right? Okay, so when you think about an electron, I want you to kind of think about a staircase. And the nucleus is down here. So this is the nucleus, right? Now electrons, and then you have this, like, you could even think about it as kind of a circular staircase, right? And it goes all the way around, right? And these are like levels, okay? So electrons can sit in certain locations farther away from the nucleus. So what they want to do is they want to be closer to the nucleus. So that's what they're going to do first. First, they're going to get in there really close to the nucleus. And so if you have, let's say, an atom that has, in this case, 3 electrons, what those electrons are going to do is they're going to get as close to the nucleus as they can. And so they're going to get on that first step of our staircase. So they're going to be as close as possible to the nucleus. And that first staircase, that first step, can only hold 2 electrons. And then we're going to move on to our next step. Now, electrons can't be in between the 2 steps. It's like rungs on a ladder. And the electrons have to be on a rung, or they have to be on a step. They can't be in between. And so that next electron is going to go to our very next step on the staircase, or our next energy level, right? Because remember, we said the farther you get from the nucleus, the more energy those electrons have. So it's going to go to the next step, the next closest step to the nucleus. And so this one electron here on our second step, or our second, we call it a principal energy level. So on the second energy level carries more energy. So look over here, see higher energy? So these on the first step are low energy, right? And as we go up the staircase, you're going to increase that energy. All right, so when we do this, what you have to notice about this staircase, I'm going to kind of erase my lines here, is that these steps aren't like the steps in your house. They're not even steps. So from the first energy level to the second, so this step right here is huge. It's a really big step. But then when we go up from principal energy level 2 to 3, what's going to happen is that step's going to get a little bit smaller. So here, this step right there, it got a little bit smaller. The next one gets even smaller. So every time you go up a step, those steps get closer and closer together. Okay? So it's not an equal distribution of distance from the nucleus. So that first step's really big, and then each subsequent step gets smaller and smaller and smaller, but it's still getting farther and farther away from the nucleus. So those electrons can occupy only certain energy levels. They can only occupy those steps on the staircase. They can't be in between. And electrons want to occupy those lowest energy levels first. That's why we put them on the first step. Then we moved on to the second step. Okay? And the lowest energy level is found closest to the nucleus. So if we look at our staircase, right, what we're going to see is right here, this is our energy level that's closest to the nucleus that has the lowest energy. And that's our first energy level. Okay? And unlike a real staircase, the energy levels are going to get closer and closer together the farther you get from the nucleus. So that's just saying that our steps get smaller and smaller every time that we move. So you just have to understand kind of the arrangement of electrons. And we're going to talk about each staircase and how many electrons they can hold. We go forward. All right. So the maximum number of electrons that can be in any given energy level has a formula. It's a really easy formula. I like this one. 2n squared. What is n? Remember, we were just looking at this staircase. Do you see here our n numbers? These are our energy levels. So n tells us an energy level. N is an energy level. Okay? All right. So in the first energy level, n is equal to 1. The maximum number of electrons present is 2. Let's see if our formula makes sense. 2, I'm going to use this formula right here. 2 times n squared. So for the first principal energy level, that's 2 times 1 squared. And remember, if anything is squared, all that's saying is it's multiplied by itself. So 1 times 1 is 1, times 2 is 2. So that's true. So in our first principal energy level, the max number of electrons, let's make a little column. Max number of electrons is 2. Let's put them in a nice neat column, right? So that's our first principal energy level. In the second principal energy level, maximum number of electrons is 8. So 2n squared. 2, my n is going to be my principal energy level. So that's a 2 squared. So remember, that's 2 times 2 times 2. So 2 times 2 is 4. 4 times 2 is 8. Okay, that works. The third energy level, n equals 3. The maximum number of electrons is 18. Let's check this last one. 2n squared. 2 times 3 squared. That's 2 times 3 times 3. So 3 times 3 is 9, times 2 is 18. So that checks out. So you need to be able to use that formula, and I don't think that's one that was actually given on your equation sheet. So you might actually want to jot that one down and say, I need to memorize that one. It's not hard. Okay. When we do this, we need to think about the periodic table, right? And how it's arranged. And the periodic table is really arranged by electrons. And our energy levels, right, that have those electrons in them are the most stable when they're full. So if I go back here for a second, when we say our energy level is full, that means we have that max number of electrons. So if the first energy level is full, that is equal to 2 electrons. If the second energy level is full, that is 8 electrons, and so on and so on and so on, right? Okay, so if we come to, this is kind of a table of what you're going to find in the periodic table. That's kind of funny. All right, so we have our elements, right? And they're ordered by their total number of electrons. So we're starting here with hydrogen. Hydrogen only has 1 electron. And then we go to helium. Helium has 2 electrons. And so we're going to look at where those electrons go. So remember, our electrons are going to go into the lowest energy level possible first. Okay, so hydrogen only has 1. So hydrogen's 1 electron has to go in the first principal energy level. So we have 1 electron in the first principal energy level. If you go to your next element, helium. Helium has a total of 2 electrons. And how do you know how many electrons are in each of the atoms? Oh, that periodic table doesn't show you. Oh, man. But when you look at your periodic table, what you're going to see, I think I have a printout over here somewhere, right, is your number at the top. Whenever you're looking at your periodic table in the back of your textbook, the one that looks like this, you're going to look at the top, and that atomic number, right, your atomic number is equal to the number of protons, which is equal to the number of electrons. Okay, so that's where you're looking to get numbers of electrons. Let's go on to helium. Helium, you gotta go across the periodic table to the other side at the top. Helium has 2 electrons. And remember, we said the maximum electrons in the first energy level, max, is equal to 2 electrons, right? So we can put another one in there. Well, helium, we put that one in there. Great. Now what happens when you get to lithium? Lithium has 3. So lithium is going to have 2 in the first principal energy level. Where's that next electron going to go? It's going to go in the next energy level, the one closest to the nucleus. And so that is the second energy level. So we have 1 electron in the second energy level and 2 in the first. And it'll go on. So what you'll notice is that these 2 were in the first period, right? Now, lithium, when you get to lithium, lithium's going to transition from the first period, look at your periodic table, should have that out, it's going to go all the way. We got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. These are all in our second period, right? So what do you think is going to happen? In that second period, guess what energy level we're putting electrons in? We're putting electrons in to that second energy level, right? Until we're full. Now we have a full second energy level, right? When did we go from the first period to the second period? When we filled full first energy level. So what you're going to see is every time we fill an energy level in the periodic table, we go down and make a new period, right? So sodium's our very first element on the third period. What do you think is going to happen? Right? Here's our first electron that goes in principal energy level 3. Then we're going to go magnesium, aluminum, silicon, right? We're going to go all the way down until we hit argon. So what we see with these is that we're increasing our number of electrons until we get to a complete third principal energy level, right? So that's how the periodic table is organized, such that every time you fill a principal energy level, you are changing the period. Okay, so that's what you should really take away from the periodic table, is that it's arranged by electrons. Okay, so why is that important? Well, if you know how many electrons are present in each energy level for an element or an atom, you can tell how that element is going to behave. So elements that have the same number of electrons in their outermost energy level are going to behave the same way. So they're in the same group, and that's why they're in the same column. Remember, a group is a column. So look at, their example is boron and aluminum. So if you look at your periodic table, where is boron? Boron should be in group 3A, right? It's boron, and then right underneath boron is aluminum. So boron's 5, aluminum's 13, right? That's their numbers. So even though they have different atomic numbers, they all have 3 electrons in their uppermost energy level. So let's go and check that. Boron and aluminum, right? Here's aluminum. Aluminum has how many electrons in its outermost energy level? It has 3. We call these outermost electrons, we call them valence electrons. So I abbreviate that VE with a minus, valence electrons. Well, let's go look at boron. Boron, here's boron. Boron has, guess what? Look at this, 3 valence electrons. So even though they have a different total number of electrons, they have the same number of electrons in their outermost energy level, which is the definition of a valence electron. And that's what controls the chemical behaviors of all of our elements, right? So an cool thing is that you can look at the group number and you can determine how many electrons are in any given element just based on their group number, right? So, all right, so this is what we already said. I'm kind of like getting ahead of myself. I'm too excited about this. So we said the highest energy level that contains electrons, those are our valence electrons, our valence shell, our valence level. Valence means the outermost, right? So valence electrons are the farthest from the nucleus. And these are the electrons that are going to move, that are going to be shared, that are going to be given up or taken, and that kind of stuff when we make compounds. So our groups, like I was saying, indicate our number of valence electrons, whereas our periods, on the other hand, tell us our outermost energy level. So if we looked at our example, right, both boron and aluminum are in group 3A. Well, if they're in group 3A, then I know I have, guess what, 3 valence electrons. But boron is in period 2. This is period 2, whereas aluminum is in period 3. So boron has 3 valence electrons in the second energy level. Aluminum has 3 valence electrons, but in this time they're in the third energy level. Okay? All right, so we did that. So here's kind of a condensed version of the periodic table, right? We know that our groups tell us the number of valence electrons, but there's a caveat. There always is, right? That's only true for our main group elements. So our main group elements are those that have the A, right? Those are our main group elements. So if you look at the periodic table, that is not including all of these transition elements in between. It's different. those can have multiple, they can have multiple states, and so you don't exactly know how many valence electrons they have depending on how they're configured. So we'll talk about some special cases later, but we're going to learn just about the easy stuff first, right? So our groups tell us our number of valence electrons. Our periods tell us the principal energy level. So you can take any one. Let's take calcium here. So calcium is in group 2A. That tells us calcium has 2 valence electrons. It is in period 4. That tells us we have 2 valence electrons in the 4th energy level. Okay? So you could do that with any of your main group elements. That should be pretty easy, right? Let's look at some other elements. Let's look at group 8A. If we look in group 8A, let's talk about helium. Helium's kind of our exception here. You have to be careful because helium does not have 8 electrons. We just said that. Helium only has 2. So really helium kind of should be over here. But the reason that we put it on the other side of the periodic table is because it has a complete outer valence shell. So helium only has 2 valence electrons, but those 2 valence electrons complete the first energy level. So it's very, very, very stable. So if you have your outer valence shell full, you're super stable and you're very unreactive. So helium is stable. Hydrogen is not. Helium is. If you go down, neon now is going to have 8 valence electrons. Argon has 8 valence electrons, right? What else can we say about these elements? We can say helium's 2 valence electrons are in the first energy level. I'm just going to abbreviate that EL, energy level. Neons are in the second energy level. Argons are in the third energy level, right? So you have in that last row your noble gases. And remember, your noble gases are very stable. They don't want to react with anybody else because they have all the electrons they need. And so if you go down, what you're going to notice is that everything except for helium has 8 valence electrons. And so we call that an octet. So if you have 8 valence electrons, that is an octet. Remember, oct is the prefix for 8. So it's an octet and it's very, very stable. And that's what all the elements want to get. They want to get that octet. They want to be stable and basically complete. Okay, so let's go back to our notes, right? So elements in group A are noble gases, are inert gases. They're unreactive, right? So all of our noble gases have 8 valence electrons except for helium. But helium, right, does have a complete energy level. So it's the first energy level and it has 2 valence electrons. So most atoms are going to react in order to get that octet. They don't have it yet and they want it. So they're going to react and they're going to get their octet. So how do you do that? Sometimes you're going to give away electrons, sometimes you're going to take electrons, and sometimes you're going to share electrons. And so depending on how you do it, if you share, you're a covalent compound. If you give and take, you're an ionic compound. And so how you get that octet tells you what kind of a compound you're going to be. So let's talk about give and take first. Give and take's kind of the easiest one. Oh, but we're going to go do some problems. Okay. I'm getting too far ahead of myself. We got to go do some problems. What we're going to try and do is identify how many electrons are in each energy level of our following elements. So we're going to start with helium. So if you remember, if we come back up to our periodic table, right, here's helium. Remember that even though helium is in group 8A, it only has 2 electrons. So where do those electrons have to go? They first go into the first energy level. So remember, it's in period 1, and we only have 2 electrons, so that's where they're going to go. So our total number of electrons is 2, right? Now, where do they go? That first column is how many we have, and then the next columns are going to be where do they go? And I guess I should kind of separate that so this is a little easier to look at. Okay, I'll do that with this too, so that when we do it in class, it'll be done. Okay. All right, so we have 2 electrons. We're going to put them in the first energy level. Now, if you don't have anything in the columns, you can assume that's 0, right? So carbon, our next one is C, carbon. Here's carbon. We have a total of 6 electrons. So let's go fill it in. We have a total of 6 electrons. Where are they going to go? Well, you can only fit 2 in that first energy level. So we're going to put 2 there. How many do we have left? 6 minus 2 is 4. So those 4 electrons are going to go in the second energy level. Let's move on to sodium. Look at sodium. Sodium, we have a total of 11 electrons. So let's go put them in. We have 11 electrons. So where are they going to go? Well, we're going to put 2 in the first principal energy level. Now we need to go on to the second energy level. We're going to put 8 in there, right? 2 minus 11, we have 9. So we just put 8 in the second energy level. We still have 1 more. And that 1 more is going to go in the next energy level, and that's going to go in the third energy level. So just make sure that all of these right here need to add up to your total, right? So 8 plus 1 is 9, plus 2 is 11, and that works out. So just be careful about that. Okay, neon. If we come over here, here's neon. Neon has 10, I don't know if you can see that, 10 electrons, right? So we're going to come down, we're going to give it 10. Well, I didn't want to leave my highlighted things. That's okay. Okay, so 10. So I have to put 2 in that first energy level. Me and technology today, come on. I don't know why it's not working. Okay, 2 in that first energy level. So that gives us, we had 10. So 10 minus 2 gives us 8. So that second energy level will take 8, and that's it. That's all you put. You gotta stop because you got 10 electrons there, okay? So practice knowing where you can put them, and you have to know the maximum number that can fit. You have to know that first can only hold 2. That second can hold 8, right? And so on and so on. Okay, the next one. How many valence electrons are present in the following atoms? What you want to do is you want to go up to your periodic table. So I have nitrogen. N is nitrogen. Okay, so let's erase what we've done. So we have nitrogen right here. When we want to know how many valence electrons, where are we looking? We're looking at our group. We're in group 5A. So that tells us that we have 5 valence electrons. That's that simple. All you have to know is what group it's in. So this is in group 5A. Remember, if it's an A, it's a main group element, so you can do this. It's 5 valence electrons. Boron. Boron is in group 13, or group 3A. And so group 3A has 3 valence electrons. 3A has 3 valence electrons. It's going to be so easy. Silicon, go and look. Si. Si is right here. Si is in group, you're right, group 4A. Okay, so I'm going to come down and I'm going to do group 4A. Gives me 4 valence electrons. K. Potassium, right here in group 1. So if it is in group 1, 1A, it's also group 1, but also 1A, 1 valence electron. Okay, pretty easy. Oh, I should have done the other one, but that's okay. So we'll do 3.4 in class. All right, I I think I'm supposed to be doing the odds. Yeah. Okay. Which of the following elements is stable as atoms? So when we say stable, what are we talking about? Filled outer shell. So remember, that's either, it's usually 8 valence electrons, except for helium, which is happy with 2 valence electrons. So what do we got? We got hydrogen. Hydrogen's only, this is group, right? 1A. So how many valence electrons? He has 1 valence electron. Is he stable? Nope, not stable. Sad face, right? Neon. Neon is group. Neon is group. I want to come back and show you. Neon. Am I doing neon? No, I'm doing nitrogen. Neon's the next one. I'm doing nitrogen. We already did nitrogen. We said nitrogen is 5A. Neon's our next one. Neon's in 8A. So let's go and write those. Group 5A, group 8A. So if you're nitrogen and you have you're in group 5A, you have 5 valence electrons. Is that a complete octet? Nope, not stable. Group 8A. Ooh, neon. Neon has 8 valence electrons. Yay, it is stable. So C is stable. Sodium, if we go up and we find sodium, sodium's right here. Sodium is in group 1A. Where am I? There we go. Group 1A, that tells me I have 1 valence electron, and I'm not stable. So my only one that was stable out of all of those was neon. All right, so then we're going to pause here, and it'll be section 2 in the next video.